The course today is concerning the coastal zone. The name is Coast on the Move, Introduction to Coastal Landscape. There is two parts. The first one, basic knowledge on wave and currents. So, ocean waves form primarily under the action of wind, which transfer its energy to the water surface. The first undulation appears as small ripples, which then grow depending on wind speed, wind duration, and fetch, that is, the distance over which the wind blows without obstructions. The fetch concept is very important to know. You should understand that if you take the wind speed, of course, you do not have the same waves if the wind speed is on 1 kilometers, 10 kilometers, or 100 of kilometers. So it's very important to realize that the fetch is the distance where the wind has an action on the ocean. So at the end, waves can grow up and they can fall and they can move to the shoreline. So we're gonna see all the transformation during this travel. So we should clearly define the wave characteristics, and because a wave is a kind of undulation of the water surface, and we define the wave by the 8 in meter here. After by the seconds, I mean the period. Sorry, this is the period explained by the units is seconds. The wavelength, the distance between two crests, and the direction. So on the ocean, of course, the waves are not always the same. So we need to define the elevation by a simple indicator. And there is several. The first one is the best one, the more useful is the significant wave 8. This is this one. These indicators are more close to a medium aspect, and this one are more close to extreme wave 8. You should keep in mind that during a storm, if we define the storm by the significant wave 8, an extreme storm in the Mediterranean Sea, let's say around the 6, 7 meter 8. So the extreme is around 10 meters. So it's very important to know which data set you are using and which terminology and how the waves are calculated. So these waves are coming from the offshore and moving to the shore. And there is a lot of process which affect the waves. So we divide offshore waves and intermediate and shallow water and waves. This limit is defined by a depth, which is something like half of the distance of the wavelength. You see in this graph, there is undulation of the waves. In the offshore, they're symmetric. Close to the shore, they become dissymmetric. And at the end, they're breaking. So in the offshore, you can consider that the wave characteristics, more or less, they stay identical. They do not change a lot in first approximation. So under deep water swell conditions, waves propagate without changing their characteristics. This is the first order of approximation. If you have offshore wave data, you may assume that wave properties are conserved. However, during wave 8, wavelength and direction begin to change as soon as water depth decreases. And this transformation starts when the water depth becomes less than half the wavelength. Initially, the modifications are gradual, but they increase progressively as the wave approaches to the coastline. There is several concepts to know, and the first one, very important one, is refraction and shoaling. So we're going to speak about refraction, but few words about diffraction. because diffraction is the bending of waves around obstacles and through gaps, allowing energy to reach saturated areas behind barrier. And this phenomenon redistributes wave energy and affect wave height patterns in the harbor or behind groins or close to the headlands. We have a very fast change in the wave direction. Another process very important is shoaling. And the shoaling occurs when waves enter shallow water, causing their speed to decrease and their height to increase. So this process conserves wave energy while compressing wavelength, often preceding waves breaking at the shore. This process is very important just before the breaking process. There is also bottom friction, and bottom friction slows waves as they interact with the seabed in shallow water and dissipating energy. It reduces wave height and can influence sediment transport near to the shore. After the waves are breaking, and we will discuss later about the wave setup. On this slide, you can see wave crest. The wave crests are on the red line. This is the red line. And the wave crest, you see, represent a storm. We are in a small area close to Marseille, and there is a lot of pocket beaches in this area. And to understand wave refraction, it's essential to analyze how these wave crests are formed. If you examine a single crest, you see that, for example, here it is deeper than in this area. For example, this point is 10 meter depth, and why this one is around a 5 meter depth. But the velocity of the waves and at the end the wavelength is more important when it is deeper than when it is shallow. So there is a kind of changing of direction. And if you have a look on all the wave crests, you see that along the line, the bathymetry is not always the same. So there is a kind of, let's say, the wave crests try to be the same than the bathymetry. So there is a change of direction. So this is refraction. What we can do when we have these results is to build some things that can represent the wave energy. Because you see that you should keep in mind that the refraction has a very important influence on the wave direction. You see that there is a change of wave direction. What we can do is a conceptual, and it's not you cannot see that on the field. Is that we can quantify the strength of wave crest by representing energy, and we represent energy with orthogonal lines between each wave crest. This concept is known as wave orthogonal. So if we draw an orthogonal line from crest to crest, we observe that some orthogonals diverge here, and some orthogonals converge in that part, okay? But the energy is the same if you are between these orthogonal, the energy is the same than in this area. So here, there is less energy because the distance between the two orthogonals is more important than here. And it is opposite on this part. So this is why in this part, the wave height will be higher, and why in this part, the wave height will be lower. Another example, a very well-known example for engineers, because this example is very important, because there is a port there, and this port was constructed before we know well the wave propagation mechanism. So the breakwaters collapse under the action of longer periods waves. When we analyze the bathymetry, we observe a lobed formation, okay, deeper. Here it is a crest line, and now if you have a look, you see that the crest line are changing a lot, and they here, for example, they are very different than on the offshore. So if you build the orthogonals, by calculating these orthogonals, we find that the maximum of energy concentration occur precisely at the breakwater in the front of the port. Thus, the representation of wave propagation demonstrates significant practical values for coastal engineering and risk assessment. You see that all this energy in the offshore during the energy on this distance is the same on this small distance. So the waves were very important and break the breakwaters. Well, so the method of representing a refraction and waves orthogonal is in fact somewhat a little bit outdated today. On the left side of the graph here, you can see an older modeling approach where intersecting orthogonals lead to invalid calculation. In this area, calculations are false. This limitation arises because the method assumes uniform wave energy between orthogonals. And this is a strong limitation. And modern coastal engineering now, or geomorphology, or oceanographers, they are using models, for example, SWAN model, Mike 21, or Telemark, and so on. And they are more connected to a spectral analysis of the waves, and they incorporate spectral energy, distribution, and phase average wave physics to overcome these issues. So these tools provide either accuracy, particularly in complex bathymetry or under variable wind and current condition. But keep in mind that, however, orthogonal method remains highly practical for two key reasons. Pedagogical value, of course, it is more intuitive, and it's also a fast and rapid assessment for preliminary analysis or educational purpose. What you should try to do is to have a look on the bathymetry and imagine if there is convergence or divergence of orthogonals and non-wave energy. This is resumed by this slide. So we have just seen that the wave crisps tend to adapt to the bathymetry. This means that by simply visualizing the bathymetry and knowing the incoming wave's direction, you should be able to determine whether wave 8 will be amplified or reduced. In this figure, the bathymetric contours are flared outward. As a result, wave 8 will be lower in this area, okay? So you already have done this observation. In the bay, the waves are smaller. And this is a way to explain why there is sediment at the end of the bay, because there is not a lot of wave energy. And like this, you can explain why there is a pocket beaches. And we will speak about pocket beaches later in the lectures. If you have a look on this bathymetry, you see that it is completely different, and there is two islands. And if you modelize and simulate wave crest and wave orthogonals and wave angle, also you can define here an area where the waves are not so important. And behind island, we know that sometimes it's possible to see some tombolos. We will explain what is tombolos later on the other lectures. It is the same for a spit. And you see this is a spit, a sand, this is sandy, and this is the crest line, okay? And you see that the crest line are moving, so we should be able to reproduce this changing direction. Like this, we can simulate the angle of incidence, the longshore sediment transport, and explain how the speeds are growing. Well, now we can continue to move close to the shore, and we can speak about the surf zone, because it is in the surf zone that the process are strongest. So have a look on this figure. You see that here we call that the point of breaking, and after between this point to the shoreline, this is the surf zone. And sometimes you can define outer surf zone when the waves are breaking, because it's done in several meters, on the inner surf zone. So there is several morphologies of the waves when they are breaking, and just to know that sometimes they are spilling. Look at these photographs. Sometimes they are plunging. Surfers are using plunging waves, and other waves are breaking very close to the shore. We are calling them collapsing and surging. Well, very important is the current in the surf zone, because they are very strong. So few information about that current. We can define three main currents. The long-term current, the first one, which is the stronger. And this current appears when the waves are coming with a small angle to the shoreline. If it is perpendicular waves, you do not have this current. This current is parallel to the shoreline. Okay, this is the shoreline, and here is the current. You see the waves are coming. There is a angle of incidence. Probably the good one is a 20 or 30 degree. And like this incidence and the breaking induce a current, very strong, the long-term current. And as the waves are breaking, and as there is a current along the shore, the sun can be carried on by the current. For example, you see along this red line, this is the sun transport. And you see that the sun transport is, of course, connected to the current, but is connected to the wave breaking. On this part on the ball, there is a breaking. The waves are breaking on the ball, and after, sometimes they reform and they can break close to the shore. So the current is along the shore and very strong, and probably the more important current to know. Another current, which is not along the shore, but which is directed offshore, and this one contributes to loss of sediment, or can contribute to that, is the undertow. So the undertow is, have a look on this figure. You see that this is the water envelope, and the waves are coming from that point to this one. And here is the undertow. We'll have a look on this line. If the current is on the left, it is offshore directed, and on the right, it is onshore directed. Undertow is the current following offshore near the seabed, the surf zone. It is only in the surf zone. And it is mainly driven by waves set up at the shoreline. And it's a kind of compensating current from the onshore mass transport by wave crest and wave walls. You see that there is onshore mass transport, and it is more or less if the water need to return, and this return is the undertow. The undertow affects all the surf zone. And of course, it is connected to the intensity of the wave and the wave height. On this figure, you see that the wave A are moving, and if you have a look, the undertow is something like that. Another very important current, well-known current, is a rip current. And these two photographs are very famous. They are from my colleague Andrew Short, and are very clear to evidence this current. On this one, you see in this area, this is a current, this is a rip current. Rip current are offshore directed, connected to the surf zone, and they cross the surf zone, they go offshore, but they start a few meters after the surf zone. In that case, this is a pocket beach, and the rip current is connected is in this area along this rocky port. And there is what we're calling a neck, sorry, of the current. And after, when the current velocity decreases, the sediments are deposited like this, in this form. In these pictures, you see that here is the presence of the rip current, but they also are present in the morphology. They start close to the shoreline because of process. The waves are crossing on the swash zone and they are moving offshore. So they are well known because they are very dangerous. They can carry on swimmers very offshore. And if there is a rip current, most of the time there is some information concerning these currents. So probably you already meet them on the beach. But it's nice to speak about current, but on the field they are mixed and the situation are quite complex. So this first figure describe longshore current. This is the beach, and the waves are coming with a little angle of incidence to the shoreline, and there is a current along the shore. In that case, there is no wave angle of incidence, and thus there is a lot of rip currents here and there. And sometimes, with a little angle of incidence, you can combine both longshore current, of course, undertow, and rip currents. And so there is a mix of currents, and you should have a very attention. You should be a very you should have the eye of the geomorphologist to observe that. So when we are moving after the surf zone to the shoreline, the area is what we call the swash zone. You see, the swash zone is the movement of the water which is going on the sea and retreat after. And you see that this movement is moving up and going down. When it is moving up, we call it sometimes the swash and the uprush. And the return is the backwash. In this example, you see that there is a little wave angle, there is a little angle of incidence. So the sediments are moving like this and like that, like this and like that. And it's possible to transport along the shore sediment. It's important to understand how this area works during fair weather condition and during storm condition. You see that, for example, during fair weather condition, this is the water level and this is the beach, and you see this line is the water table. And because of the small waves, the water table is low under the sand. And you see that when the waves are coming with the uprush and after they are going back with the backwash, and there is a lot of infiltration because the water table inside the sand is low. So sediments can go in there and stay there. And sometimes there is a kind of laminar sedimentation in this area. And this process can explain the beach recovery during a fair weather condition. But during storms, the waves are stronger. So the swash movement are stronger. And the water table is more elevated because of the sea water, which is a little bit higher. So there is not this movement of infiltration that I just explained on swell and fair weather condition. During storms, there is uprush very fast and there is a backwash very fast. So as the backwash is very fast, there is erosion in this part of the beach. So this is the way we explain the beach erosion during storms. Well, to conclude, we have examined the generation of a wave offshore, their propagation in deep and intermediate waters, their breaking, and the process in the subzone. However, the water elevation that ultimately determines coastal erosion and marine flooding. And the water elevation is a key concept to understand erosion and marine flooding. So this is on this graph, this is the beach and this is the dune. And you see that there is several influence to define during a storm the water elevation, which is here. This is the sea level. On first, during a tide, the range of the tide in the Mediterranean Sea can be 10, 20, 30 centimeters, sometimes 1 meter in the north of Adriatic, for example, or in the Tunisia, but it's not so common. And during a storm surge, there is a kind of atmospheric pressure which is down, and there is strong winds. So the result is an impact, an elevation of the water level with the pressure and with the wind. Another process, which is the wave setup. And when the waves are breaking, as wave break, water pile up on the shore through a process called setup. Because of the breaking, at the end, on the opposite to the shore, there is a little elevation. Not so little, because the wave setup in Mediterranean storm condition can exceed half a meter. And at the end, there is the run-up. Finally, as wave rush on the beach, the maximum vertical reach or run-up can be 1 meter. So at the end, if you make a kind of total of all this process, the wave 8, not the wave 8, but the water elevation on the beach can be 1 meter elevation, 2 meter elevation, 2 meter and a half. So you can create, in that case, a lot of coastal flooding and dune erosion. Well, so now we discuss about the process from the offshore to the shoreline. So many thanks to you. I hope you enjoy my French accents and you follow me for the second lectures.